pendulum is composed of a particle as of mass 500 grams attached to the end A of a massless inextensible cord OA of length 1 meter. The other end of the cord is attached to a fixed point O. The pendulum is shifted from its equilibrium position by an angle of 37 degrees, and then S is given at time 0 an initial velocity perpendicular to the cord and of magnitude 1 meter per second. The particle reaches the lowest position B with a speed of magnitude 1.5 meters per second. The horizontal plane containing B is considered as a reference level for gravitational potential energy. Let's move to part 1. Determine the initial mechanical energy of the system as cord Earth. Initially, the particle is at position A. Then mechanical energy at position A equals 1/2 mva squared plus mgza. Now we need to calculate the value of za. Look at the figure. This is za. A prime B equals za. Now examine the figure carefully. Look at OB. A prime B or ZA equals OB minus OA prime. Then consider this right-angled triangle. Cosine 37 equals OA prime over OA. Then OA prime equals OA cosine 37 degrees. Replace OA prime by OA cosine 37. You will get this equation. Look at the figure. OA equals OB, and it is equal to 1 meter. Then replace OB and OA by 1. You will get 1 minus cosine 37 degrees or 0.2 meters. Now we are ready to calculate the mechanical energy at point A. Plugging in the numbers gives the value of this mechanical energy. It is 1.25 joules.
1-2. Prove that S is subjected to air resistance during its motion between A and B. When S is subjected to air resistance, then the mechanical energy at B should be less than that at A. So let's determine the mechanical energy at B. ME at B equals 1/2 mvb squared plus mghb. Since B belongs to the reference level of gravitational potential energy, then HB equals 0. Therefore, the mechanical energy at B equals 1/2 mvb squared. Replace m by 0.5, Vb by 1.5. Therefore, the mechanical energy at B equals, or approximately equals, 0.56 joules. Since the mechanical energy at B less than that at A, therefore S is subjected to air resistance between A and B.
Let's move to part 1.3. The work done by the tension force exerted by the cord is 0. Why? Look at the figure. We draw the tension force in 3 positions during the motion of S between A and B. The tension force is perpendicular to the direction of the displacement of its point of application at any instant. Then the work done by the tension force is 0 at any instant. Let's move to part 1.4. Calculate the work done by air resistance between A and B. We know that the change in the mechanical energy equals the sum of the works done by all the non-conservative forces acting in the system. The only non-conservative force that does work during the motion of S from A to B is the friction force. Then delta ME equals the work done by the friction force. Delta ME equals MEB minus MEA. Plugging in the numbers gives the value of the work done by the friction force, which is minus 0.69 joules.
Focus, please. This is important.
Number 2. When S reaches point B, The cord gets cut and S moves along a horizontal surface until it reaches the bottom D of an inclined plane. Suppose that friction is neglected along BD. 2.1. Prove that the speed of S remains constant along BD. Since the friction is neglected along the path BD, so the mechanical energy is conserved. The expression of the mechanical energy between B and D is given by 1 half mv squared plus mgh, but the height of the particle along the path BD remains 0. Then the mechanical energy becomes 1 half mv squared, but the mechanical energy and the mass remain constant. Therefore, the speed of the particle between B and D also remains constant.
When S reaches point D, it starts its motion along the inclined plane DC, which makes an angle of 30 degrees with the horizontal, with an initial speed of magnitude 1.5 meters per second. The friction force acting on S along CD has a constant magnitude of 1 Newton. Let's move to part 2.2. Determine the distance dk traveled by S before it stops along the inclined plane. Let's use this equation. The change in the mechanical energy between points D and K equals the work done by the friction force between these 2 points. Delta ME equals the final mechanical energy minus the initial mechanical energy. Replace the mechanical energy at point K by 1 half mvk squared plus mghk. 1 half mvk squared equals 0 because S stops at point K. Now we need to calculate HK. Look at the figure. HK and DK forms a right-angled triangle. Sine 30 equals HK over DK. Then HK equals DK sine 30. So replace HK by DK sine 30. The mechanical energy at point D equals the mechanical energy at point B because along DB the speed is constant, so the kinetic energy is constant, and also the gravitational potential energy is constant. Replace F by 1 Newton, then dk equals 0.16 meters.
Part 3. Determine the thermal energy produced during the motion of S between A and K. We know that the work done by the friction forces result in transformation of the mechanical energy into thermal energy. So, the thermal energy, or W thermal, equals the absolute value of the work done by the friction forces. But the variation in the mechanical energy between A and K equals the sum of the work done by the non-conservative forces between A and K. But the friction forces are only the non-conservative forces that do work between A and K. Then delta ME equals the work done by the friction forces. Then the thermal energy equals the absolute value of the variation in the mechanical energy between A and K. Delta ME between A and K equals MEK minus MEA. MEK equals the kinetic energy plus the gravitational potential energy. But the kinetic energy at K equals 0. So MEK equals mghk. MEA equals 1.25 joules proved before. But HK equals dk sine 30 proved in the previous slide. So HK equals 0.08 meters. Then replace M by 0.5, G by 10, and HK by 0.08. So the thermal energy produced between A and K equals 0.85 joules.